All right, hello again, everybody. So in this video, we're going to look at the same bag data structure that's covered in the vector-based bag one, which you probably want to have like either watched or read the notes for first, because I'm going to reuse a lot of the code from that. Excuse me. But we're going to build it on top of a dynamically allocated array. So when we build a bag on top of a vector, the standard library vector class does a lot of the heavy lifting in terms of like managing memory and stuff for us. So we're going to build basically like a zero dependency bag structure that doesn't require the sort of standard library. But that means we're going to have to do a lot of that sort of work for ourselves here. This one's going to be a little bit sort of like meatier in terms of like the amount of code that we present. I'm going to try and keep as much of the sort of code that we've already written the same. In fact, we won't really have to change very much of it at all. I think only one of the existing functions will have to be modified. But we will need to add a fairly decent amount of new code to handle the sort of memory management part of stuff here. All right, let's jump in feet first, eh? Okay, so the new stuff that we need to add here, the stuff that's going to change from before, right? We're going to get rid of the vector and we're going to replace it with this. It's a plain old int pointer to a dynamically allocated array that we're going to call the same name data there like that. Now the other thing we need to add is vectors track their own size. So if you have a vector, you can do dot size and it will tell you like how much stuff is in the vector there like that. Dynamically allocated arrays do not record their own size. If you have a dynamically allocated array, there's no way to ask it like, how big are you? How much stuff is in you? So that means we need another variable here to track the capacity there. So our constructor up here, that's what this is here, right? This is our constructor. That's going to have to change. So we're going to store the capacity given to us in C, in cap. Then we're going to create a dynamically allocated array of that capacity. And then just like before, we set the size to 0. So that gives us an array that is big enough to hold cap many things, 8 or 20 or whatever. But SZ records the fact that like currently we're not using any of it there. Now, most of our methods stay the same. Like only the methods that sort of like refer to the vector as a vector have to change. And the only one that actually did that was the capacity function. So in the capacity function, we're using data.size because data is a vector. In the new version, data doesn't have any dot operations on it. That's why we had to add the cap. So in the new version here, we just returned the cap in the capacity function. All the other functions can stay exactly the same. They don't need to change at all. They weren't using any particular sort of vector operations on data. We don't have to change any of the other functions other than the capacity function like that. Now that's assuming that you were using like the capacity function wherever you wanted to get the capacity, right? If your code was sort of littered everywhere with references to data.size, in all of the sort of rest of the bag class there, then you're going to have to go through all of those places and replace all of them with cap. But if you were using the capacity function, you don't have to sort of do that. So that's why, like in when I wrote the code for the vector-based one there, I preferred to sort of use these functions like full and empty and capacity and size rather than accessing like the sort of private member variables directly, because it simplifies this process of sort of changing how things work under the hood there like that. But now we need to worry about memory management. Like, when does that array that we created get destroyed? So like every time we sort of say new this or something, right? Every new should have a corresponding delete somewhere in the program to release that memory, to sort of give it back to the system to use for other purposes. And then a related problem is what happens when we make a copy of a bag? If we do something like B equals C, where B and C are both bags, we expect the contents of one bag to sort of be like copied into another there. Before, the vector class handled all of this for us. So it handled like, cleaning up after our sort of memory and sort of destroying stuff. It handled copying stuff from one to another. Now that we're sort of doing this with a dynamic array, we have to worry about doing these things ourselves here. So we're going to add code to basically say, how do we destroy a bag? And then add code to say, how do we copy a bag? How do we copy one bag into another there like that? So just to sort of review like how memory works here, when you create a normal variable here, like if you have 3 variables inside of your main here, int x, y, and z, those get placed on a part of memory called the stack here. I'm making up the addresses here, right? Real addresses on the computer don't look sort of like nice, tidy numbers like that. Also, ints take up 4 addresses. So if I was being realistic, this would go 1000, 1004, 1008. I'm just sort of simplifying stuff to make it presentable. So if you just create a normal variable, then it ends up on the stack there like that. And the thing about the stack is it gets cleaned up automatically. Like I don't have to say when I'm done with X, when I'm done with Y, when I'm done with Z. The memory for these variables will just sort of go away and be given back to the system automatically when they are sort of done here like that. Again, here I'm just talking about like how some of the stuff that I'm simplifying when I present memory, right? Ints take up 4 addresses, different things take up different amounts of space. If you print out an address, if you just see out an address, you'll see that like they're actually huge numbers there. There's a bunch of like stuff that I'm simplifying here just to kind of make it be presentable. So, if you want to be a stickler, read through this list and I'm probably covering whatever you're talking about. But I'm just trying to make things understandable. So when we declare a normal variable here, like we say, int x like that, when we hit the closing curly brace for that function, X is removed from the stack. So the sort of part of your program where a variable like exists and you can talk about it is called its scope. The scope of X is from there to there, from sort of up here where we declare it to down here, the sort of closing curly brace. That's the part of the program where you can talk about X, right? That is also when the program is running where X is taking up memory. So when X sort of like comes into scope here, that's where X's memory is allocated. Scope. Here. And then down here, where X goes out of scope, a variable that is not in scope, there's no way to refer to it, so it's free. The computer is free to sort of release the memory that's attached to it there. So that is where X's memory is sort of released there like that, at that sort of closing curly. You can't write a program where you don't have the right number of closing curly braces, right? It won't compile. So that means it's impossible for you to like forget to release the memory for a stack-based variable. You have to have the right number of curly braces in your program. Normal variables get deleted when you hit their sort of like owning closing curly brace there like that. So if all you're using is stack-based memory, you don't have to worry about like memory leaks or anything like that, right? Your program literally won't compile if you are sort of like not writing it in a way that wouldn't release all of the sort of memory accurately. But dynamically allocated objects, like anything that we create with sort of new, those are located in a different part of memory called the heap here. Heap objects, you create them with new, and they're not tied to any particular pair of curly braces. So they only get destroyed when you say they should get destroyed by using delete on them there like that. You can create a heap-based object with new in one sort of part of your program and then delete it in a completely different part of your program. They're not tied to any particular scope, any particular pair of curly braces. That lets us do some interesting stuff with like objects that kind of like live from one part of the program into the other, but it also means that we have the responsibility of making sure that they get deleted when we're sort of done with them there. So like here's an example. Let's say that we create a pointer to an int here. We're just going to sort of step through this program like one line at a time and see how like stuff sort of evolves here. So initially we're going to set p to null pointer, but then after a little bit of work, we're going to dynamically allocate an array of size 4 and then set p to point to that. So we hit this line of code here. This is where p is allocated. P itself is a normal variable and it lives on the stack. So over here on the stack, we have an address dedicated to p, and currently its value is a null pointer there. Then when we get down here, we ask for 4 addresses on the heap, enough space to hold 4 ints, like that right there. And then the first address in that block becomes the value of p. So p is sort of like this pointer to this array of 4 addresses that we've created over here. So this is where we've sort of said, hey, I need 4 ints worth of space over here on the heap. Please find me enough room for 4 ints there. Like that. Now, when we hit the bottom of this function, right, this curly brace here marks the end of p's scope. So the address that belonged to p on the stack, that goes away. But we never called delete on this array, so it is still out there taking up space. If we call this function like a bunch of times, we call this function in a loop, every time we run it, it will claim another 4 ints worth of space. Run it enough and we'll run out of heap space. Our program will sort of run out of memory here. So this program here has a memory leak. You know, in a program that you only run once, you might not even notice, but in a program that's sort of like running for a long period of time, it'll just sort of use up more and more and more and more memory until eventually it just runs out completely there. Okay, so in this case, like what I should have done was before p went out of scope, right, before I hit the end of this function, I should have deleted that array. I have to do that before p goes out of scope, because once p goes out of scope, like p, I can no longer use it in my program, right? So somewhere before this sort of closing curly brace at the end of this function here, I should have done delete square brackets p here. If you use new with the square brackets, if you create like an array, then when you delete it, you have to use the square brackets to delete the entire array there like that. When we're done here, right, we have this sort of like chunk of 4 ints worth of space that I asked for and never gave back there, like a memory leak over here on our heap. And there's no way for me to like delete this stuff later. Like once p goes away, p was the only thing that sort of knows what address this thing is at. When p is gone, I have no way of getting to this. So I can't use it for anything else, but my program still thinks that it belongs to me because I never deleted it there. Now, another thing to sort of bear in mind is when we copy a pointer, that doesn't copy the thing on the other end of the pointer. So this is a sort of similar setup here, except in the middle of this, I'm making a copy of the pointer here. So again, like let's step through this sort of like one line at a time and sort of see what happens here, right? So same as before, this is where p gets created. So p's scope is from there to there. And at the same time, we're going to dynamically allocate 4 ints worth of space on the heap here. So my stack contains p, and my heap contains this array. And p points to the array. When I go down here to q, so the scope of q is from there to there. P is still in scope. There, right? So q goes on the stack, but I don't get a copy of the array. What I get are just 2 things that point to the same array. Right? I only have one sort of array of 4 ints over here on the heap. I don't have 2 separate arrays there like that. Over here on my stack, I have 2 pointers pointing to the same thing there like that. If I want q to be a copy of that array, I have to do that manually. I have to do another new int 4 over here, and then I have to do a loop to copy the 4 things from P's array into Q's new array there, like that. Copying a pointer does not copy the stuff on the other end of the pointer there. When we get down here, both P and Q go away, right? But again, same deal as before, I still have my memory leak over here. I know at no point did I sort of release the memory like that over there, right? So what I should have done over here is I should have said, I want to delete the memory associated P. Or, right, I could have said, I want to delete the memory associated with Q. Either one of those two things would be fine, but you don't want to do both. Because I only have one array down here. I don't have two arrays, so I only need one delete. It could either be the delete for P or the delete for Q, but I don't want to delete the same array twice. Deleting the same array twice is like an error, and it'll usually crash your program or make things sort of screw up in a weird way there like that. So just because I have two pointers doesn't necessarily mean I need to delete both of them. The number of deletes in my program is based on the number of news. If I have only one new, then I'm going to have only one delete, no matter how many pointers I have pointing to that particular thing there. So this is just emphasizing like the sort of, that we have the same address here, right? So when both P and Q sort of like existed, P pointed to address 80,000, and Q also pointed to address 80,000 here. So even though they're separate variables, right, they're different variables on the stack there, under the hood, they both point to the same thing. They both point to the same array there like that. If you use, like the way that you use a pointer, right, is you dereference it. So if I did like star P, that would take me to the same place as star Q. Or if I want to treat it like an array, if I did, P at subscript 0, that would take me to the same place as Q at subscript 0. If I do, P at subscript 0 equals 7, then that would put a 7 there, right? But that means Q at subscript 0 would also be a 7, because P and Q aren't really like different things. They're directions to the sort of same place there like that. So this is a problem for our bag class, because unless we say otherwise, this is how it will work. When we copy one bag into the other, it will just copy the pointer. It won't copy the stuff on the other end of the pointer here. So here's, again, another little setup here. So down here, we're going to create a bag of capacity 2. I'm keeping the capacity small just so that I don't have to, put too much stuff on the heap down there like that. So remember what is inside of a bag, right? So the private data section of a bag looks like this. We have an int pointer. We have the capacity, and then we have the size. So when we create a bag variable, these three things here are going to end up on the stack. So B is going to be created in these sort of first 3 stack addresses over here, right, like that. So when we create B, right, capacity is 2, so that gives me 2 addresses down here on the heap. And B's data points to that part of the heap there like that. My capacity is 2, and my size is 0 there like that. So at this point, like, B is fine. It's a small bag. It can only hold 2 things, but I can insert and erase into it, and everything's sort of fine there like that, right? But then when we create C as a copy of B, what's going to happen? Well, since we didn't say that copying needs to do anything sort of fancy, all that happens is the compiler just says, oh, we'll just copy these sort of things from B into C sort of directly. So 80,000, 80,000 to 200. So what I'm left with, right, are two bags that both point to the same array. B thinks that that is its array, but C also thinks that that is its array there like that. That means that if I insert something into B, it will appear in C, and if I erase something out of C, that will change the stuff inside of B there. They're not really proper copies. They're sort of weirdly linked under the hood. It's not sort of how you expect, copying to sort of work here. And then finally, when we get down here, right, when we hit this line, the sort of closing curly brace that marks the end of the scope for both B and also for C, the memory that they were using on the stack goes away, but their heap memory is still in use. There's no deletes anywhere in my program, so that means we have a memory leak. So we sort of have two different but related problems that we need to fix here. We need to fix the copying problem of the two copies kind of sharing data in the background. And then related to that, we need to fix the destruction problem, the way that we sort of leak memory when variables go out of scope there. The destruction problem is easy to fix, but you kind of can't stop when you just fix one of these things because they're all kind of interrelated to each other. So these things are sometimes called the big three here, because once you sort of start adding them, you kind of can't stop. Like if you need one of them, you probably need all three of them. So we are going to add a destructor. That's a function that says, all right, how do you destroy a bag? What needs to happen when we hit that sort of curly brace there? Right now, what happens when we hit a curly brace is nothing. We need it to delete the sort of array that's under the hood there like that. We're going to add a copy constructor, which says, how do we make a copy of a bag into a new bag? Like, what is this line like there? What does that need to do that it's not sort of already doing? And then related to that is copy assignment, which says, how do you copy a bag into a bag that is already there and has stuff in it? In other words, if you do this, if C already existed and I wanted to copy some other bag into it there, what does that need to do there? And these two, of course, are connected to each other, but they're slightly different. So that's why they're sort of separate operations there. But at a minimum, we're going to need to add these three sort of special functions to our bag class here. The destructor is the easiest of the three. It's, a lot of times it's like a one-liner here. So the destructor is always named with a tilde and then the name of your class. So the name of our class is bag. So our destructor is just named sort of tilde bag. It never takes any parameters, so there'll never be anything like inside the parentheses here. And the job of the destructor is just to undo whatever the constructor did. So remember, our constructor, among the other stuff that it did, I won't write it all out here, is it did a new, so data equals new int array of size cap. So if there is a new in your constructor, there should be a corresponding delete in your destructor. If your new uses the square brackets, then your delete needs to use the square brackets here. So this is just saying whenever a bag variable goes out of scope, whenever we hit a closing curly brace, run this code in here, which will clean up our sort of memory. That will delete our memory that we have in there like that. If you only have one new in your constructor, you only need one delete in your destructor there like that. So usually the destructor is pretty easy, unless of course you're sort of creating many things, and you might need to have a loop to delete everything or something like that. But we can't just stop with the destructor. If you add the destructor and you run like a program like this, your program will probably crash. And that is because when we hit this closing curly brace, right, what is going to happen? Well, we have B, and then C is a copy, but put copy in quotes there. not a real copy of B. In other words, both of these things are going to point to the same array here. So we're going to have what's called a double free. We're going to delete the same array twice. A double free is an error, right? Like it either crashes your program if you're lucky, or it breaks things in some weird way and your program crashes like sort of later on there like that. So once we add the destructor, we can't just sort of like, stop there. We have to go on and add the copy constructor. The copy constructor handles situations like this. And then we have to add the copy assignment to handle just sort of like, regular assignment-based copies there like that. That's why these things are sometimes called the big three. Why the big three are the big tree? No, who wrote that? Again, I got hacked. They messed up the H key on my keyboard, but I fought them off and it's fixed now. So we need a copy constructor. Copy constructor basically says, what does this line of code do here? This is a variable declaration. We're declaring a variable named C, which means C is being constructed. This line is exactly equivalent to this line down here like that. And this makes it look more like a constructor. We've got the parentheses. Normally inside the parentheses, we would put the capacity, but now we're putting the sort of original, the thing that we're making a copy of there like that. So the copy constructor has to do two things. It has to allocate its own heap memory. It can't just copy the pointer. We don't want to have two pointers pointing at the same thing. It has to give itself its own separate new chunk of memory. And then it has to copy everything from the original into the new one there. And this is going to involve a loop here to copy all the stuff in the array there like that. So this is what our bag constructor is going to look like, but we'll go through it sort of line by line here to sort of dig into why it sort of looks the way it is. So this is a constructor, and constructors always have the same name as the class itself here. So the name of this is bag, and then its parameter list is just one thing here. So this represents the thing that we are making a copy of there. Like, what's the thing that we're making a copy of here? And we take it as a reference, because if we didn't have the reference on it, then how would it get into the function? It would get into the function by having a copy of it made. But we're defining what it means to make a copy. So without the reference, we would be basically saying, okay, step one of copying a bag is make a copy of a bag, and that, like, that's sort of circular logic. That doesn't work. We have the reference on it to say that, hey, orig is just like a link back to the original bag here. It's not a copy of it there. But when you copy something, you don't change the original, right? Like when you put something on a copy machine, like it doesn't change. We have the const on here to basically promise that we're not going to modify the original. We're not going to change orig. We're just going to sort of look at the stuff inside it and duplicate that stuff there. So you can sort of identify a copy constructor as it's a constructor that takes a const reference to the same kind of thing as the class itself is there. Cap and sz, those are just plain old ints. So I can just copy those directly. So we just say whatever the original's capacity is, that's going to be my capacity. Whatever the original size is, that's going to be my size there like that. Like any sort of thing that is not a pointer, that's just like a regular old variable, you can just do a straight up this equals that kind of copy there. But data is a pointer. So what we don't want to do, right? What we don't want to say is my data is just a straight copy of the original's data, because that gives us two pointers that point at the same thing, and we don't want that. So what we're going to do is we're going to create our own array, same capacity as the original, like that right there. Now, initially, this array doesn't have, like, it has numbers in it, right? But they're just whatever random values happen to be there in memory. So then the second step of this is I have to loop over the original array and copy each element of it one at a time into the new array there like that. You can't just do like, data equals orig.data. That won't copy the array. That will just copy the pointer. To copy everything in an array, you have to loop over the array manually and copy everything from one place to another there like that. So that is the sort of definition of our bag copy constructor there. Again, like let's try this out here with just sort of like some example code and sort of see what happens here. So imagine we have this code in like our main or whatever there like that. What's that going to do? So we have a bag of capacity 2. Right? That is this one over here. Sorry, that arrow looks like it got sort of messed up there like that. I'm not sure what like that. And then we're going to copy that down here into C. So we copy this capacity here just into there, like that's a regular one there like that, right? Then we copy this size down into there like that. No change about that. But then when we hit this line right here, we're not just going to copy this 80,000 down into there. That's the thing that we sort of don't want to have happen. Again, I don't know why this arrow is messed up there. Instead, we create our own separate array over here at a different address. So 90,000 belongs to C, 80,000 belongs to B, there like that. And then, why are you over here, arrow? Pretend, you know, again, I can't. Pretend you didn't see this. Not there. I'm not doing a very good of like hiding my mistakes. So then this loop runs and it copies the -7 from one array to the other. So what I'm left with are 2 separate dynamically allocated arrays owned by 2 separate bags there like that. And this is what we want, right? Because now modifying B does not affect C, modifying C does not affect B, and you can delete them separately and everybody's sort of happy. Everybody's kind of ready to go there like that. Copy assignment is related, and it's kind of easy to sort of mix up copy assignment and copy construction here. But copy assignment is used when you're copying into something that already exists here. Imagine we create a bag B and then we create another bag C. Now at this point, B and C aren't related to each other at all, right? There's no copying happening. And then I say I want to copy C into B. So this is different from what we did before. Like in the previous one, we were doing this. We were doing bag C equals B. So in this case, C does not already exist. Like C is coming into existence and we're copying B into that. What we're doing here though, B already has stuff in it, right? Like I've inserted stuff into B, it's already got stuff in it, and then I'm wanting to basically overwrite it with the stuff that is inside of C here. So that's where this is a little bit different, is in copy construction, you're copying into a thing that didn't already exist. So it's like a blank slate. You don't have to like clean it out or anything like that. You can just sort of copy into it here. But here we're copying into a thing that is already being used for something else. So the first thing we have to do is sort of clean it up, like empty it out, and then we can copy new stuff into it there. Usually the copy assignment is kind of like a combination of your destructor and your copy constructor. So the first thing we have to do is clean it out. We just destroy everything in it. So we basically do whatever the destructor would do. And then once it's sort of destroyed, it's like a blank slate again, and we can copy everything into it by doing whatever the copy constructor would do. This isn't quite like the safest method to do this, because if something goes wrong sort of like in between these two steps here, then we've kind of lost the stuff that we had before we copy new stuff into it there. So there's a bit of a safer way to do this here, but this is kind of like the way that's sort of, you know, easy enough to understand here. So all you really do is, here's the code for my destructor. And then down here, here's the code for my copy constructor. It's basically just a sort of like a copy and paste job of the code of those two functions in here. The copy assignment function looks a little bit gnarly, like it's like we're returning a reference and like we got this and we've got this and a bunch of stuff in here. But all of this other stuff is just kind of boilerplate. It's always the same when you write a copy assignment here. And then the sort of core of it is just copy and pasting the two other functions. This first little bit that's highlighted up here at the top is a check for self-assignment. So if you do something like, A equals A, which I don't know why you would do that, but like, it's not invalid, like it's not illegal. That shouldn't do anything, right? That should do nothing if you copy a thing into itself there. But if you were to just run this code down here directly, first we would delete A's data, and then we would try to make a copy of it, but it's already been deleted here. So if we just ran this code directly without sort of checking for this situation, then bad things would happen. So up here, this is just checking to see, are we doing a self-assignment? And if so, we just straight up return without doing anything. Then we do the destructor code, right? We sort of like clean ourselves up. We empty ourselves out to prepare for new stuff being copied in. And then we run the copy constructor code and dump all of that stuff in there so that it's done there at the end. So here's the big three that we're sort of left with here. You have destructor, you have copy constructor, and then as a combination of those two things, right, we have our copy assignment over there like that. That is the code that we would need to add to our bag class if we want to get rid of the vector class and make it be sort of memory safe there like that. Now, I mentioned previously, like the way that we sort of wrote the copy assignment as step 1, destroy, and then step 2, copy, right? That's not the safest way to do this. Because if something goes wrong in between those two steps or as like part of the copy, we've already deleted our original stuff and we can't sort of get it back. So there's another way to do this that is called the copy and swap, where you basically make the copy first and then only sort of like swap it out for the original after we're certain that the copy sort of like completed successfully. So that looks like this. This is an alternate way to do the copy assignment here. So we're going to rely on the copy constructor that we've already written to make a copy of the original up here like that. So copy is a copy of the original there like that. So assuming that that copy works correctly, we then swap our stuff out. So this is me and copy is the copy. So I swap all my stuff for all the stuff in the copy. And then when we hit this line down here, that runs the destructor for the copy variable. But when we hit this line down here, the stuff inside of copy is no longer the copy. It's now me. It's now my stuff because we sort of swapped with it there. So it's like we're sort of trading places with the copy. And then when the copy is destroyed, it's not the copy anymore. It's my stuff there. So that just sort of changes the order so that the copy happens first and the destruction happens only after we know that the copy happened successfully. So we swap our stuff with the copy. Now we're the copy and the copy is us. And then when we hit the end of the function, it deletes the copy, which is my old stuff there like that. So this is a little bit sort of safer than the way that I wrote it, but it's not just like an easy copy paste job there like that. Now in 2011, C++ added move semantics, so that goes from the big 3 to the big 5. Now we saw that like your program basically won't work unless you have the big 3 in there. Like things will sort of break if you're missing the big 3 and you're doing like any kind of dynamic allocation here like that. The big 5, though, the sort of 4th and 5th functions, those are optional. All they do is make some things faster, but you can leave them out and your program will still sort of work here like that. I'm not going to test you on like the move semantics or the sort of 4th and 5th ones here, but basically what they do is they have to deal with not making copies in certain situations where we would normally make a copy. So for example, like let's say that we have something like this. So we're going to create a couple of bags here. Okay. And then we're going to do a ternary operator. We're going to check some condition, right? And depending on whether it's true or false, we're going to give a copy of A or B here. So either A or B, right, is going to get copied from the function into C here. C is being declared, so that means this is going to do the copy constructor. Okay? To copy either A or B into C here like that. But what does returning from a function do? It ends the function. So that means as soon as the function returns, both A and B get destroyed as soon as the function ends like that. So basically, like we're sort of like a two-step process here, right? Step number one is copy. And then step number two is destroy. And those happen like one after another. There's nothing that sort of goes in between them because we're literally returning the thing, making the copy of it there like that. So the idea of move semantics is if you're in this situation where it's like copy return, we can steal instead of copying because we're going to destroy the thing right after. So nobody will notice if we just sort of steal its data. So what we're going to do is we're going to sort of mark a function as like, hey, this works in this particular situation here, where whenever we sort of see a value that is going to be destroyed, instead of doing the normal copy process, we'll just sort of cheat and steal its data. And that avoids the sort of loop that would be needed to copy everything from one place to another here. We'll sort of simplify this example down to just like this to avoid the sort of ternary operator here. So you can imagine this is like making a copy of A into C there like that. This doesn't actually use move semantics. There's an extra compiler optimization that sort of like eliminates the copy automatically without us having to write any code. But you can kind of imagine that, like, you know, between C++11 to C++17, this would have sort of done that kind of like, oh, we can avoid the copy and if we write the code to sort of do the sort of theft part of it there like that. So without move semantics, here's the sort of process that happens, right? We create A with capacity 10, so there are, you know, sort of 10 addresses over here on the heap. And then A sort of stuff, again, like the arrows are kind of in the weird place here, is that. So we do the work to copy all of these things here from there down to there. When we return A, we copy from A into C up here like that. And then we destroy A. So A down here like goes away, and we're left with the copy there in C there. So instead of doing that, since A is going to be destroyed right after the copy is done, let's just let C steal A's heap memory. Like there's no way that could cause a problem because we're going to destroy the other one as soon as we're sort of done here like that. So move semantics is just a way of marking that, like, you care about when this situation occurs and you want something special to happen. So our move constructor would handle that situation, and it looks like this. This little fancy thing here, that says that we are interested in the situation where this object is going to be destroyed. It's an X value. It's an expiring value there like that. So whenever we see an object that, like, oh, we're copying something, but it's going to be destroyed, run this code instead of the original copy constructor. Again, like just like before, we can copy cap and sz directly, but down here, there's no loop, right? There's no new creating our own array. Instead, we just steal the array directly from the victim, and then we give the victim a null pointer after we're sort of done there like that. And we can do that because the victim is going to be destroyed as soon as this function is done here. There's no way that, like, some other part of the program would notice that we've kind of done this sort of, like, you know, sneaky swap in the background there like that. So if we do it now with the sort of move semantics in place here like that, right? You know, we still copy cap and sz like that, but we don't create a separate heap array down here like that. all we do is say, you know, that array doesn't belong to you anymore. Now it's mine. So I just steal the pointer to the array and give it to C out here like that, and A is left with a null pointer. We have to put something in A's data so that when A's destructor runs, it has, you know, something to destroy. So we just let it destroy null pointer, which doesn't do anything at all there like that. When we hit the sort of like, you know, curly brace that marks the end of this here, again, like that runs the destructor, but all we're doing is deleting the null pointer, so nothing happens. The array still exists, and C points to it. That lets me avoid a loop that, you know, if you had like a really big bag, right, that loop might need to copy a million things from one place to another, and we replace that with just those two lines right there. So if you wanted to go and do like the whole big 5, you would add a move constructor and move assignment. And move assignment, like just like before, is a combination of your destructor, and then this code here is literally just your move constructor. Right, so it can just be sort of like a copy and paste job there. You could also go with the safer sort of like move and swap version if you sort of want to do that, but that's the sort of basics of it there like that. So again, I'm not going to test you on like the sort of like the move construction stuff there like that, but all of the assignments after assignment 1, so assignment 2 and later, require all of your code to be memory safe there. Like it won't pass the tests if you're leaking memory, if copying doesn't work the way that it's supposed to. So in any assignment where you are, you know, using new, you're manually allocating memory, you will have to worry about adding the big 3, the destructor, the copy constructor, and the copy assignment overload there like that. All right, so that, like, between the sort of 2 versions of our bag class there, that's kind of like our review of classes and a little bit of a review of vectors. If you want, we're also going to do a little bit of review of like the string class, so you can look at the string splitting notes and video to get a feeling for how that is going to work there if you want. But that'll do it for this.